So far we've talked about covalent bonds being the sharing of electrons, and today I'm going to tell you about how those electrons are not always shared evenly, and that's how we can have nonpolar covalent bonds and polar covalent bonds. Right, so the uneven sharing of electrons is based on the fact that really covalent bonds are more like a tug of war over electrons than they are sharing. And so how good an atom is at pulling the electrons toward itself is called the electronegativity, and that determines which direction the electrons are going to be moving. So if two atoms have exactly the same electronegativity, then they're going to be shared completely evenly, and that's going to be called a nonpolar bond. So a nonpolar bond is when the two atoms share the electrons evenly, and a polar bond is when the electrons are shared unevenly, and the uneven sharing of electron results in a dipole. So a dipole, di meaning two, and poles meaning ends, means that there's two different ends to the bond. So one end of the bond has more electrons than the other one, and so the end with more electrons is going to have a partial negative charge, and the end with less electrons is going to have a partial positive charge. Okay, and over here I've shown, in the top corner here, I've shown the elements that we use the most often, and you can see that the one with the highest electronegativity is fluorine, and as we move away from fluorine, the electronegativity goes down. So the farther you get from fluorine, the lower the electronegativity is. So for our sake in this class, what we're going to assume is that unless I tell you otherwise, if the two if the two atoms in the bond are different, then you can automatically assume that it's going to be a polar bond. Whereas if you have two atoms that are the same, then you would assume it's a nonpolar bond, because if the atoms are the same, the electronegativity for each of them is going to have to be the same. Okay, so as an example, this is one of the things you might have to do with this information. List the following bonds in order from least polar to most polar. So the least polar bond is going to be the ones that have the electronegativities that are the most similar, and the most polar bond is going to be the two atoms that have electronegativity differences that are the most different. And you can see for each of these bonds we have a fluorine as one of the elements that we're bonding to. So we have a fluorine here, 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 and here. All right, and then over here on our diagram, I'm just going to circle the other ones. So we have fluorine, which is the one I said we're looking at in all of them. We have phosphorus, we have sulfur, we have gallium, and we have germanium. Okay, so those are the four different ones that we're looking at. And you can see, as I said in the previous slide, as you get farther away from fluorine, the electronegativity gets smaller. So the least polar one is going to be the one that is bonded to fluorine that has the electronegativity that's closest to it. So sulfur is the closest to fluorine on the periodic table, and it's also got the closest electronegativity. So the SF bond is going to be the least polar, and then phosphorus is right next to that, so the PF bond will be next. Germanium is right here, GE, that is going to be the next, and then the most polar one is going to be the gallium fluorine bond, because there's a difference of 2.4 electronegativity between them, between the 4 and the 1.6. So that's going to be the most polar bond of the four that we have listed. So if a polar bond is the uneven sharing of electrons, a molecule that has polar bonds in it would have an uneven distribution of electrons. So a polar molecule is going to be one where the electrons are unevenly distributed, and a nonpolar molecule is going to be one where they are evenly distributed. And you're going to have to look at this in terms of the whole molecule and whether it has polar bonds or not. So if there are no polar bonds present in the molecule, then it has to be nonpolar. If it has polar bonds, then you have to determine if they result in an uneven distribution of the electrons. So we're going to do an example just to make this a little bit clearer. Okay, so we want to classify each of the following as either polar or nonpolar. We have water, we have CO2, and we have formaldehyde, H2CO. Okay, so the first thing we need to do is draw the Lewis structures for each of these. So at least the water you should be able to do on your own, but I'm going to go ahead and draw them here. So the oxygen is in the middle, and we have two hydrogens coming off of it, and there are two lone pairs on the oxygen. Okay, the carbon dioxide, we have the carbon in the middle. We have a double bonded oxygen on one side and a double bonded oxygen on the other, and the oxygens each have lone pairs, but there's no lone pairs on the carbon. And then finally, the formaldehyde, we have the carbon in the middle. We have a double bonded oxygen off of one side, and then we have the two hydrogens also coming off of the carbon. Okay, so in these cases, what we need to know is what is the three-dimensional structure of each of these. And so this is why the molecule shapes that we learned earlier in this chapter are so important, or one of the reasons. So if you didn't know the shape, and if I hadn't drawn it this way, I guess, the water molecule could look like it's symmetrical. It's got a hydrogen on one side and a hydrogen on the other. However, water is a bent molecule, so it looks like this. Okay, because these two lone pairs up here push those hydrogens down. Okay, oxygen is much more electronegative than hydrogen, and we use arrows to show which direction the electrons are traveling. So the electrons in this case are traveling up toward the oxygen in both cases. And so what that means is we get a lot of electron density up here and not a lot down here. So this is not symmetrical, and these polar bonds are going to make it a polar molecule. So this one is polar. Okay, for carbon dioxide, oxygen is more electronegative than carbon, so our oxygens are going to go these, or our arrows are going to go these directions. And since carbon, I should have mentioned this earlier, since carbon doesn't have any lone pairs on it, it's a linear, carbon dioxide is a linear molecule. Okay, so this bond angle is 180 degrees, and so the two oxygens are both pulling electrons away from the carbon, but they're doing it in a way that's even. So if you have two really strong guys on either side of your tug of war, if their strengths are the same, then the middle of the rope doesn't go anywhere. Okay, so this is a case where we have polar bonds, because the carbon-oxygen bond is polar, because they have different electronegativities, but we do not have a polar molecule. This is a non-polar molecule. So I'll write an NP here and a P here. Okay, and then the last one we have is formaldehyde. Okay, carbon doesn't have any lone pairs on it, it just has these three groups, and when you have an atom with three groups coming off of it, they just form the trigonal planar, which we talked about before. The hydrogen and carbon are not so different in electronegativity. The main difference here is going to be the oxygen, which is going to pull the electrons up this direction. And since it pulls the electrons up that way, you should be able to see that you're going to get an uneven distribution of electrons up here, and this is going to be a polar molecule as well. Now, the last thing I want to mention is just that polar molecules, because they have charges, are attracted to each other. And we're going to get into this a lot more in the next chapter about what those kinds of attractions are called, and how you can make predictions about them. But one thing to notice is that because they're attracted to each other, they stick together more than molecules that are nonpolar. And so the question is, how would this affect the boiling point? And the answer would be that we would expect that ones that stick together more are going to stay in the liquid phase longer than ones that don't stick together, and so that would cause the boiling point to be higher, so you would have to heat it up more in order to get the molecules to break apart into the gas phase. Okay, so this wraps up our discussion of polarity, and you're going to get a lot of practice determining if molecules are polar or nonpolar in this chapter and in the next chapter.